mock shellcodes and what we can do with the mock API within shellcode. If I can get PowerPoint to work. The first part of this presentation, I'm going to kind of go over the background of mock. It's been covered before in different presentations and many papers, but because of the unique architecture of the OS X kernel, you kind of need somewhat of a background on the marriage of mock and BSD. So the XNU kernel in OS X is kind of this hybrid kernel. It's based on both mock and also based on BSD. So it's not really truly just a BSD or a Unix derivative. Mock, for anybody who's not familiar with it, was developed originally by Carnegie Mellon. It was a true microkernel was the concept. So as far as the microkernel architecture, only really the lowest level, what needed to run in kernel space or in ring 0 ran within the kernel. Everything else was developed as servers or services for the kernel in user space. So things like networking, file systems, all of these things that traditionally in monolithic kernel would be part of the kernel were actually user space services. Only things like virtual memory handling, hardware access, those kind of things were actually in the kernel itself. FreeBSD, on the other hand, is a traditional monolithic kernel. The OS X kernel is based, the BSD portion of the OS X kernel is based on FreeBSD 5. And again, just conversed to the microkernel statement, a traditional or monolithic kernel kind of packs everything into the kernel space. So all OS services that you might think of being provided by the kernel are running in kernel space in ring 0. This would include drivers, networks, stuff, file systems, all of that kind of thing, as opposed to the microkernel model. So you can see they're kind of diametrically opposed to each other in a lot of ways. That kind of paradigm, and so it kind of makes for a pretty strange Frankenstein marriage between the two models. This diagram kind of shows, it's from Wikipedia, which we know never lies. So this kind of shows the layout of some of the different services available within OS X. And you see here, this is the kernel with XNU. You have the BSD portion and the mock portion. This is kind of a little bit clearer breakout. So you see that the BSD layer actually lies on top of the mock layer. So while the mock layer handles things like interfacing with the hardware, IBC, RPC, kernel threads, interrupts, memory management, scheduling, the BSD portion handles things like networking processes, like traditional Unix processes, file systems, crypto, security, those type of things. So there's different portions of the kernel that handle different functionality. So since this talk is talking about, is going to go into shellcode within the Mac operating system and primarily talking about using mock in your shellcode. We'll look just for a second at kind of the traditional way of writing shellcode for OS X. This is just, you can probably see it's not a very functional shellcode. It exits. But it's a good example of an OS X shellcode. You see we're simply calling a BSD system call for sysexit and then leaving. Nobody? No. So mock, the background on mock and how it works, there's some kind of abstractions or kind of concepts that you need to cover in order to understand the inner workings. Mock is made up of tasks and threads and also ports and port rights. So tasks, a mock task is really a bundle of resources. A task has a virtual address space, something called port rights or a port namespace, and also can contain mock threads, which are actually the unit that will actually execute some sort of code. All code execution happens within mock threads as opposed to within the task itself. So everything has to have at least a task and a thread. BSD processes are kind of an abstract on top of mock tasks and threads. So every BSD process that you see when you run PS on an OS X box has a containing mock task underneath. And also it's important to note that mock threads are not the same as P threads or POSIX threads that, if you're familiar with multi-threading programming. So this diagram kind of shows just kind of the layout of some of the elements of a traditional OS X process. So here you have a mock task underneath with mock threads. You have a virtual memory space assigned to it, and you have a port namespace. And then you have the BSD element that allows the BSD portion of the kernel to know what it is, so a process structure and things like that, so that it has a process ID and can run and be recognized by the BSD portion of the kernel. Mock tasks also, in that port namespace, have what's called ports. Mock tasks hold ownership of ports and port rights. So in order to communicate with a mock task, you use ports. And the kernel identifies if you have the ability to communicate to a mock task by the port rights that you own. A port with a mock task is a unidirectional communication mechanism. So it's kind of like a one-way pipe in order to communicate with mock tasks. Port rights are access control. So there are 3 different types of port rights. There's a receive write, a send write, and a send once write if a task allows another task to send only one time to that task. This kind of just shows a breakdown of how mock tasks can communicate with each other. Mock is very much built upon IPC mechanism, and we're going to go over that IPC and RPC mechanism as far as incorporating it into our shellcode. But this kind of shows we have 2 mock tasks or BSD processes, and these mock tasks can speak to each other and can also perform operations on one another if one task has a port right to another task, depending on the rights that are allowed. So this you can also transfer between mock tasks. You can transfer port rights. You can also transfer data or shared memory, and also control other mock tasks via IPC. So if we look at this, we see it kind of, it looks a lot like a network communication, client-server type of communication that we're pretty familiar with. In fact, the original mock IPC, not in OS X, but the original mock implementation, was built to be machine independent. And so you could perform this communication and IPC across network boundaries and host boundaries, so that you could more like a traditional RPC call. OS X removed that functionality, so we can't perform mock communication, IPC communication across the machine boundary. Dino in a talk a couple years ago at Black Hat, introduced Machiavelli, which was basically re-implemented that functionality in order to perform IPC calls across the network. Pretty cool. So we can see, let's see. Sorry. So for performing these IPC calls, OS 10 provides an API for performing communication between mock tasks. And one of the cool things about mock is that you can manipulate other mock tasks as long as you own port rights for that mock task. And also, the kernel is just another mock task. And so in certain under certain conditions, you can actually manipulate the kernel and the kernel's memory space, et cetera. A few useful mock functions are task for PID, which basically will return a port right for a mock task identified by a specific Unix PID. This port right then allows us to perform other tasks like manipulating that task, et cetera. So then we can do things like VM write, VM read, VM allocate, which will allow us to read, write, and allocate memory in the target task's virtual memory space. Which, if anybody who's familiar with general exploitation or memory corruption bugs, if you can read and write to another process's memory, then you have pretty much full control. There's a lot of other functionality too available within this API, and they're in the GNU, the XNU source /OSFMK/man. There's man pages to go over the different functions that are pretty useful. I'll just go over a couple just as an overview. VM write like I said, VM write allows us to write to a target task's memory space. So we can change values, we can inject code, we can do whatever within the target task's memory space. So it takes it as arguments the target task, which we retrieved via task for PID likely, the address to write to, what data to write to, and the size of that data to write to, to write. VM read does, it's pretty self-explanatory. Ouch. It reads from the target task memory space. So again, it takes the target task, the address to read from, the size of data to read, where to read to in the current task's memory space, and the data that was actually returned is returned in the data count. VM allocate it allocates memory within the target task. Again, familiar arguments. I'm going to just demonstrate quickly using the API, the mock API, how to. Oh. I have problems with PowerPoint. How we can allocate memory in another task on OS 10. Oh, great, I can't see anything. So I'm going to go ahead and, let's see. So we see this pretty simple C program, which utilizes the VM out. I don't have mirroring displays on, so. Give me a second. Okay. So you see here, we get the port for a specific PID. We allocate memory in it, and then we just run through that memory that we just allocated and do a write to that memory space just to paint it so that it's easily recognizable. So start calculator. Oh, sorry. Is that better? Sorry about that. So our PID for the calculator, So we just, to examine the memory that we just allocated, we see we allocated memory in another task and painted it with A's using the mock API. So the mock kernel has, like BSD, has the concept kind of similar to system calls in BSD. With BSD, in order to execute a system call, we place the system call number in EAX, push our arguments onto the stack in reverse order, and then execute in 80 in order to invoke the kernel and execute our system call. Mock traps, on the other hand, work somewhat similar. Mock trap identifiers, where BSD system call numbers are positive integers, mock traps are negative numbers, the identifiers for them. And instead of calling the kernel with an int80, we actually can't call the kernel with an int81. So we can see in the kernel source the list of mock traps available within the OS X kernel. So all of the names on the right-hand side are the actual traps. And on the left-hand side, the numbers correspond to the actual trap identifier. So you multiply that by -1, it's mock reply port is -26, etc. So this is just an example of how to execute a mock trap then from assembly in order to for shellcode. We move the trap identifier into EAX. You can see there, and then execute in 81. For there, we're calling task self trap. Down below here is a little bit more complex trap. And here we're doing, we're actually passing arguments for task for PID. So we push them onto the stack in reverse order, push the trap identifier into AX and execute in 81. What you notice from the listing before, when we're comparing mock traps to BSD system calls, if we look at BSD system calls, there's a lot of useful calls. There's over 300 BSD system calls that can be executed in that way. So lots of things that we would traditionally use in shellcode, things like the write system call, read system call, fork, exit, socket, listen, connect. All of those system calls are available within BSD. Conversely, on the other side, we have only 34 mock traps. So we look at the available mock traps, things like task self trap, task for PID, clock sleep trap. It doesn't look as useful to us as payload developers. So we have to look a little bit deeper if there's anything actually useful within mock from a malicious payload perspective. The APIs that I was talking about earlier, VM write, VM read, allocate, if you look closer at them, those mock APIs are actually just C wrappers on the client side around the mock IPC mechanism. So there are lower level IPC calls in order to execute more interesting things. The mock interface generator, or MIG, is a stub generator for mock IPC. So if you're developing a client-server interface in mock, there's a lot of plumbing, just like most RPC implementations. There's a lot of kind of redundant code and plumbing that you don't really want to necessarily worry about. And so mock implements MIG in order to take care of that. MIG is a definition language. You can you make a MIG specification file to specify the communication between the client and your server, and then run MIG, and MIG will then generate the C code that can be linked into your client and server code. As you're looking through the kernel source, what is open source left of the OS X kernel, you can look for .defs files, which are traditionally MIG definition files. So if you're looking through the kernel and trying to identify how the IPC mechanism works at a lower level, you're not going to find references directly within the mock directory for VM read, VM write, as they are. But once we run MIG, there are a lot of definition files, MIG definition files, under OSFMK mock. So when we run MIG star.defs, and then we grep out declare send RPC, which is a statement for the different MIG identifiers, we can see there's a lot more interfaces exposed through that IPC. So taking the previous example of VM allocate, we can look through the generated code and identify what the actual message structure looks like for a legal IPC call. We see that there's a mock message header, there's an NDR record, there's then below that in our request payload, we have the address, the size, and the flags, which translate to the arguments that we're actually passing to the mock API. A little bit of a closer look. This is the actual structure being filled out. So we see where in the box you see the original definition for the VM allocate call, the target task, the address, the size, and a flag for allocating it anywhere within the target's address space. We see those corresponding values here within the request header. The address, the size, the port of the target task, which is that target task argument, and then an RPC message ID. So mock RPC messages are identified, the interfaces are identified by these message IDs, this message H_ID within the request. So that's how we know what interface we're calling when we actually call the kernel. We can also see, if we look closer, that this VM allocate structure or function is actually using mock message. So we create this message header, and then we call something called mock message in order to actually perform the IPC task. So this is a breakdown, let's see, of the request and the reply structures. And in order to actually implement this, we fill out our address, which this is where the return, the target task will return the allocated address to. The size of the memory that we want to, the amount of memory we want to allocate, and what flag. So this is in this case, the anywhere flag to tell the target task to allocate our memory anywhere within the target address space. Then we also fill out things like the actual the request ID, our reply port, because tasks are, again, unidirectional, and so our ports are unidirectional, and so for it to reply, we have to hand over a mock reply port. And then this is actually sending the request, the different arguments to mock message. So the thing to remember about sending RPC messages via mock is each kernel RPC interface, we have a unique number to identify what kernel interface we're trying to call when sending an IPC message. That's denoted by this head.msgh_ID and the identifier for the actual interface that we want to call. So in this case, 4800 is mock VM allocate. So if we look in the kernel source, we can identify, or we can find the different identifiers and interfaces that are available for us to use. Each IPC call or interface has a different structure for the request and reply. And so in order to call and set up legal RPC calls at a lower level, we can look at those sources in order to identify what the structure is for the particular interface that we want to call. So looking back at the list of mock traps now, we didn't originally see anything that was super interesting. But several things do pop out. Things like task self trap, mock message trap, mock message overwrite trap, and task for PID. This kind of builds up the foundation for how we can actually construct mock IPC messages and RPC calls to execute mock RPC functions. So, if we look a little bit closer at the actual structure of VM write now, the VM write interface, and calling it with one of these traps within our shellcode, we have a mock message header. We have the body, data, an NDR record, the address to write to, and the size of the data we're trying to write to. So if we put this in, if we write with the C API, VM write function, and put it in GDB, let me actually pop over here. Actually. So we see when utilizing the C API, if we break on the actual call to mock message overwrite and print the structure, the IMP structure, the request header or request structure. This is the original layout of the structure, and this is what we see here in GDB. So we can start correlating how that structure looks in memory. The actual message header bits for the interface call, the address to write to, the size of data to write, etc. If we look at the actual region of memory on the stack, we can see the breakout here too for the actual request structure. So what's in blue is the header, what's in orange is the message body, the data portion, the NDR record, the address to write to, and the amount of data to write. So I'm going to show a little example and walk through an example here of writing to kernel memory. Remember, I talked about manipulating other tasks, and the OS X kernel is just another task, mock task. And so as long as we have the appropriate port rights, we can also write to the OS X kernel as well and overwrite kernel memory. As an example, what I'm going to use is, if you're familiar with current.secure level within BSD systems, the whole idea behind secure level is that an administrator can set the secure level of the system, and once it's set, short of there being a reboot, even someone running as root cannot reduce the security level of the system. So you see here with the syscontrol, tuning the current.secure level syscontrol, it's 0 here. We set it to 1 as an administrator, and now it's 1. And if we try to set it back to 0, it's not permitted, even though we're running as root. Now, this particular target within kernel memory, this isn't a novel target as far as demonstrating this. Actually, Nemo from Feline Menace originally came up with this and wrote about it back in Uninformed Volume 4, as far as overwriting that particular target in kernel memory, subverting the BSD portion of the kernel by interfacing with mock. The reason I chose it as an example, though, as opposed to walking through some more complicated examples, is that it's simple. It's writing a single value to a kernel address. We don't have to illustrate and walk through and parsing linked lists, et cetera, in order to unlink or hide processes or TCP ports. I've shown that in prior talks about OS X rootkits. And also, there's a pretty clear demonstration of the impact of it because if we go back to this original diagram, we see that within the BSD portion of the kernel, that's where security and access control, for the most part, are taken care of. But here we're interfacing with the mock portion and interfacing with the IPC and RPC portion of the mock aspects of the kernel, which in turn can invalidate the security controls within the BSD portion of the kernel. So to do this in C, it's pretty easy and straightforward with the published mock APIs. If we get the address of secure level out of the mock kernel, and we write a simple C program that gets the task for the task port for the kernel process ID. We see task for PID. 0 is the process identifier for the kernel task, and then where to return the port. And we write to that particular address just a value of 0, for instance, to the secure level address. Then we can overwrite that value. So in order to do this in shellcode, though, it's a little bit more complicated. We have to construct valid RPC calls at a lower level. So the first portion of our shellcode calls task self-trap, task for PID on the kernel task, and gets the mock reply port for our current task. So we see task for PID being called here. The kernel, the port write will be stored in ECX after we've requested task for PID. We're setting here the value to write to kernel memory, which is 0 for a lower secure level. The address of secure level within the kernel task. Here I'm just using a underflow in order to avoid nulls in the shellcode. And here's where we start constructing our actual header request for the IPC call. We push the address of data to write onto the stack, the message body contents, the header contents, the value of the local port here, the flags, and then finally we call mock message overwrite trap in order to call the kernel, send our IPC message, our RPC message to call VM write, and write to the kernel's memory space. So here's the assembly for this shellcode in whole, and here's the shellcode. So I'll demonstrate doing this. Let's see, with this shellcode. You see here, it's our shellcode mapping some memory and then calling shellcode. So we see currently our secure level is 0. We'll raise our secure level to 1. Oops. And now the secure level is set to 1 for BSD. We'll try to lower it back to 0, and even as root, you see that it's not permitted. So now we'll execute the shellcode, which will construct an RPC call and overwrite that section of memory. And so now we're back at 0. So it's a simple example, but it shows writing to the kernel memory within shellcode using the mock RPC calls. So from a kernel rootkit perspective, this can be really useful because without actually loading a mock O executable on the disk or loading a text, we can manipulate the kernel task and kernel memory to do things like we traditionally would with a rootkit, things like hooking, system calls, network lists, etc. Some common targets like IP ProtoX, which are the network protocol handlers in order to install our own handler or hook a TCP handler or something, or ICMP or anything like that. Kernel object manipulation or direct kernel object manipulation, we can remove ourselves from the global process list, all proc, remove listening ports that we have for our rootkit, things like that. Also, inline function patching, because we can read and write from memory and also allocate new memory, we can patch existing functions and functionality within the running kernel to execute our code that we want to. There's one problem from a kernel perspective, though, with the more modern OS X. As of 10.6, the kernel task and port writes to the kernel task were restricted. And according to an Apple developer on some in one of the Apple development mailing lists, they said task for PID being called on the kernel task is not supported anymore. It had been up until 10.6 on the kernel task, no matter what your privilege level or what API you use. So that kind of hampers what you can do, unfortunately, within the kernel as of 10.6. I'm hoping that there's a way around that, and I'm kind of waiting for Lion in order to start investigating that further. But still, utilizing mock within shellcode is useful even if you can't call the kernel task. Mock gives you a nice, a lot of nice interfaces for doing interesting things like thread injection, manipulating memory, even on userland tasks. It doesn't just have to be the kernel. And also, if you find yourself within a process, you can use mock to manipulate that process further, the process that you already own as well. So not only is it useful for manipulating other mock tasks. So like I said, when Lion comes out, we'll see as far as how overcoming that task for PID restriction on the kernel task goes. This is REcon, so I didn't have any IDA in this talk, so I figured this is an IDA disassembly of a hello world, just to wake everybody up. So to wrap up, really, at least what I've seen in public Mac shellcodes, it's still all BSD system calls, which are very legitimate and useful. But Mac, the OS X kernel, is a hybrid OS between Mach and BSD. And so being a hybrid OS, then our shellcode should be hybrid as well and take advantage of the functionality that we have within Mach. Thanks to Nemo for excellent research all over the place as far as from a Mac perspective. Amit Singh, who wrote Mac OS X internals. Dino, who's done good research and given several cool presentations on OS X exploitation, and also Charlie Miller. References, lots of things from Nemo. Abusing Mach OS on OS X in particular in uninformed volume 4 is good. OS X internals from Amit Singh, advanced Mac OS X rootkits from Dino Daizovi, Mach 3 kernel interfaces from Carnegie Mellon, and then also my presentation from Black Hat a couple years ago on crafting OS X rootkits is useful. Thank you. Any questions or?